Now, dilution is another way you make a solution. It's a useful method for preparing solution. Dilution simply means adding more solvent. And it's very useful for preparing solutions that have very low concentration. So solutions that have a very low concentration are said to be very dilute. So diluting simply means lowering the concentration. Okay? If you add more solvent, you are lowering the concentration, and we're referring to the concentration of the solute. Why is this important for very low concentrations? The reason is typical balances in the lab, okay, weighing scales in the lab, you call them balances, okay, balance. They're not sensitive enough, may not be sensitive enough for very small masses. Okay, typical balance, one of the most sensitive ones in an instructional laboratory, will have an uncertainty of at least 0.2 milligrams. Okay, so if you have to weigh something less than that, then you're out of luck. Okay, some substances are also more readily available in solutions. For example, hydrogen chloride is a gas. Okay, you don't want to be handling that. It's more readily available as a 12 molar solution, concentrated HCl. It's already mixed with water. It's 12 molar. So you need to prepare solutions of HCl from a stock solution that is 12 molar. Okay? So here's an example. Solution A is 10 mils of 0.1 molar sodium hydroxide. So let's say you have, here's a graduated cylinder, you have 10 mils of 0.1 molar sodium hydroxide. And to that, you prepare solution B by adding to that enough water to bring it to 100 mils to get solution B. Which of the following is true? Solution A contains more sodium hydroxide. Solution B contains more sodium hydroxide. Solution B has a higher molarity, or none of the above. Well, what are we doing when we are diluting? You're just adding more solvent, more water. You're not changing the amount of sodium hydroxide. So A is false, B is false. What happens to the molarity? Well, your volume has changed. Molarity is moles of sodium hydroxide over the total volume of solution, right? Well, your number of moles of sodium hydroxide doesn't change. No change here. But your volume of solution increases. If you have a bigger denominator, the molarity goes down. So your molarity would be lower, not higher. So correct answer for this one would be none of the above. Okay, how about this question? Which of these most likely needs to be prepared by dilution? 100 mils of 0.1 molar sodium chloride, or 2 liters of 1 times 10 to the negative 6 molar sodium chloride? Okay, you can see this is a very low concentration. You can actually calculate the moles here if you want. 100 mils times 0.1. Okay, let's figure out the number of moles. 0.1 moles per liter of sodium chloride times 100 milliliters. Milli means 10 to the negative third. So 0.1 times 100 times 10 to the negative third. That gives you 0.01 mole. Whereas the other one, you have 2 liters. So, but we have 1.00 times 10 to the negative 6 moles per liter. Multiplied by 2 liters. That gives you 2.00 times 10 to the negative 6 moles. This is a very small amount. In fact, how many grams would that be? Okay, 2.00 times 10 to the negative 6 moles of sodium chloride multiplied by the molar mass. Sodium is 22.99, chlorine is 35.45. So that's 58.44 grams per mole. And that gives us, let's see, 2 times 10 to the negative 6. So 2 times 10 to the negative 6 times 58.44, 0.0001. Okay, so It's a milligram right there. So it's 0.116 milligrams. 117. Okay? That is very hard to measure. Your most sensitive balance is in the typical instructional lab, analytical lab would be sensitive to 1/10 of a milligram. Okay, so that's below the sensitivity. That's right around the sensitivity of your analytical balance. Okay, so what you would do is you need to make some. So the answer to this question then is this one right here, B. You're going to have to do dilution. You make a solution that's more concentrated. Okay, call that your stock solution. And so from that stock solution, you can do a dilution. You can do a series of dilutions. Okay, it's a technique known as serial dilution to make progressively dilute or progressively lower concentrations. All right, here's a practical laboratory problem. You have a stock solution that's 12 molar HCl in the laboratory. That's concentrated HCl. And you want to prepare 500 mils of 0.5 molar HCl. How much stock solution would you need to dilute to 500? So you've decided you want 500 mils, and you want that to be 0.5 molar. Okay, so number of moles you need is 500 mils, 500.0 times 10 to the negative 3 liters. Molarity, let's do molarity times volume. So 0.50 moles per liter times, that's half a liter, so 0.5000 liters. Okay, so that's molarity of the stock, the final solution, right? The desired molarity times the desired volume. So that would be your final molarity and the final volume that you want. Well, that's going to have to be equal to the moles you can get from the stock. So molarity of the stock solution times the volume of the stock solution that you're going to need must be equal to that. So in other words, when you're doing a dilution, you can say M1V1 equals M2V2. This is called the dilution formula. What this is basically saying is number of moles of solute in the stock solution must be equal to the number of moles in the final solution, because once you've taken the stock, all you're doing is adding more water. So what's the molarity of our stock solution? It's 12, right? And so your volume of your stock solution is what you need to find out. How much of the stock do you need to dilute to 500 mils? So let's solve for your volume of stock. Okay, M stock V stock equals M final V final. So this is going to be equal to M final V final over molarity of the stock. Right, so our final molarity, desired final molarity, is 0.50 moles per liter. The final volume that we want is 500 mils. I can make that 500 mils if I want to, because as you can see, the units will just cancel out. Molarity in this case is 12.0 moles per liter for the stock. You can see that moles per liter cancels out. I will have my answer in milliliters. If you want it in liters, then you change this 500 mils to liters. Make that 0.5 liters. So 0.5 times 500 divided by 12. That gives you 20.8. Okay, so 20.8 milliliters. Or, since we only have 2 sig figs, it's 21 milliliters. So what do? What you do is you take 21 mils of your stock solution plus enough water to bring a total volume up to 500 mils. Word of caution, practical information in the lab. Whenever you're diluting concentrated acids in the lab, always add acid to the water. Okay, acid to water. That means don't just take 21 mils of HCl and then add water to it. You generally do not add water to a concentrated acid. When you have a concentrated acid, add acid to water first. So what you do is If you have a volumetric flask, for example, you can put some water in there. Okay, water first, and then you put your 21 mL of acid, concentrated acid. So your concentrated acid would mix, and then dilute to the mark, to 500 mL. Okay, you can add water to acid if the acid has already been diluted. Otherwise, you don't do that. Whenever you start with concentrated acid, if you want to dilute it, add it to the water first. A before W. Okay, here's another question. Rubbing alcohols, typically the one you can buy at the store, is 70% by volume isopropanol in water. How would you prepare 2 liters of 0.1 molar isopropanol in water? Isopropanol is C3H7OH. Okay, how much of the rubbing alcohol would you need? The density of pure isopropanol is 0.786 grams per ml. So here's a strategy you can use. You calculate the moles of isopropanol that you need first. And what information do we need for that? Our desired solution is 2 liters of 0.1 molar. So moles isopropanol. I'm just going to call it ALC for alcohol, okay? Moles of alcohol equals 0.100 moles per liter of alcohol times 2.00 liters. That cancels. So that gives you 0.2, I need to make that blue, 0.200 moles of alcohol. Okay? Now, you change that to something you can measure in the lab, which is grams. So 0.200 moles of C3H7OH, change that to grams, grams per mole. What's the molar mass of isopropanol? Let me do a quick shortcut here. Let's just go to molar mass C3H7OH. I've done this search earlier. Okay, it's 60.1 grams per mole. Okay, if I need more sig figs, it's 60.095 grams per mole. 60.095. So how much is that? 0.2 times 60.095 gives me 12.019. So 12.02. Okay. Keeping in mind my last sig fig is that 0 right there, grams. Okay. Isopropanol is a pure isopropanol is a liquid, so it's preferable to measure its volume rather than weigh it. So what you do is you change that to volume. Density is mass over volume. So if you want to solve for the volume, volume is mass over density. So 12.02 grams, keeping in mind that last sig fig there is the first decimal place, divided by the volume, which the density, which is 0.786 grams per ml. Okay. And that should give you how much? 12 divided by 0.786. It's 15.29, 3 sig figs, so that's 15.3 milliliters. So what I'll need to do is I find a volumetric flask. I find a container that can hold 2 liters. So that's a 2-liter mark right there. I am first going to dispense 15.3 mL of, that would be pure, okay? I don't have pure. Sorry. Okay, not there yet. That would be pure, okay? So this is pure. But what I have is rubbing alcohol, which is only 70% isopropanol by volume. Okay, let's treat that 70% as exact. So we say this is 70% of the volume you need, of the volume of isopropanol needed, of rubbing alcohol needed. Okay, since we don't have pure isopropanol, we have rubbing alcohol, which is only 70%. So you say 15.3 mils is equal to 0.70, that's 70% of the volume of the rubbing alcohol that you need. Okay, so the volume of the rubbing alcohol that you need is equal to 15.3 divided by 7.0, and that should give you 21.9 milliliters. So now what I do is this. I take a volumetric flask that with a 2-liter capacity. I put in 21.9 mils of rubbing alcohol, and then add enough water to bring it up to 2 liters. Okay, and that will give me a solution, a 2-liter solution that is 0.1 molar isopropanol. Okay, this might be a good time to stop.